Okay, so let's get started and talk about HALT here at Elite. So what I'm going to try to get through here today is, answering maybe these four questions. What is HALT? What's the best time to use it? How you should use it? What you might expect when you're running this test? Some things to plan for. I'll talk about the HALT chamber. And what is HALT, and is it just the chamber, or is HALT, is this kind of a broader definition for ways that you can provide testing that'll give you some answers about your product? We'll help you with some test planning, test prep, and things that you have to consider regarding fixturing for your HALT testing. And then finally, some recommendations, some things that we've learned over the years, and some recommendations that we want to pass on to clients and prospective clients for how we would run HALT with them. So in a way, we get this particular question a lot from our clients. They'll ask us to run a HALT test, or they'll ask us, hey, can we run some pre-compliance testing before we start this big qualification program? But all of those questions kind of boil down to this simple question here. Can you test my product? Tell me how and when it's going to fail, and do that more or less quickly and as cost effectively as possible. And it's a valid question for any manufacturer of a product. And, barring any kind of a, magic 8-ball answer that, yes, it will pass on this day or on that day, it's not practical or possible to give you an exact definition, but what we can do, and what HALT attempts to do, is to more or less work on this analogy that HALT, like a lot of other pre-compliance tests, applies a series of stresses, different types of stresses, gradually and systematically in a kind of a planned fashion, so that you can do a couple of things. One of them is to identify any of these inherent and latent design weaknesses. You want to gradually, kind of squeeze that product, pressure it, stress it, so that you can eventually find, what fails first. What is that weakest part of the design? That's really what HALT is in any kind of accelerated testing, is to, apply stresses in some manner that you can kind of learn some things about your design. So what is HALT? And kind of some simple bullet points. HALT in this presentation certainly is going to be focused on a particular type of test chamber. And here's the one at Elite with a couple of panels pulled off of it. But this is our HALT chamber. And it's in this HALT chamber that we apply temperature, vibration, other stresses like power. We'll cycle power, we'll vary the loads on the device. But to apply those temperature stresses, vibration stresses, either in combination or individually, to eventually get the part to respond, to have some sort of anomaly occur. The intent of this type of test is, again, to create this first failure, what are all of the failures, to kind of apply these stresses to figure out what's kind of lurking in this design. HALT is also used to understand margins between what might be the product specification and some of these overstresses that will eventually interact with your product and create these failures. So other purposes for HALT, again, is we'll get to those in a second here. But HALT again, it's best applied early in a product design. It can be used in other parts of the product development cycle, but when it's most productive and most fruitful is when you can kind of get down to the board level. Certainly this is focused on testing electronics or electrical components. If you can start testing a product at the board level and identify weaknesses at the board, when you can have control of how you hold that board, how you fixture it, how you can get hot and cold temperatures to it, it's really the best application of HALT. We know that that's not always practical, and it's not always done that way, and that's fine because we do find faults with products that are a little bit later on in design. But in terms of what a manufacturer can do to react to those findings, it's best if it's done early in the development cycle. HALT, what we find is it's better for some items, not as much for others. Typically, it's a pretty effective test for electronics. It's an effective test for connector interfaces. It's less of an effective test for large structural products. And it's mostly because of the nature of the vibration that's produced by this machine, the character of that vibration. And lastly, HALT is very much of a qualitative reliability test. We'll talk about that in a second here. Let me see. As we talk about the HALT applications, that again, clients come to us and we execute HALT tests for mostly these reasons. Again, to proactively find these latent defects that are existing in a product. A latent defect would be one that is not quite known to the designer. When the defect is precipitated, that becomes a patent defect. We know what that defect is. So that's our goal, is to try to locate these issues with these stresses, find them, and make them known to the designers and the manufacturers. Again, understanding operating margins, destruct margins. HALT is also used as a comparative test. A lot of clients come to us and say, I've had this particular product in the field for some years. We've improved it, or we've got a different design, or even a competitive design. And can we assess the performance of our existing design with this newer competitive product that we have? So it's used for that purpose. I'll share with you information a little bit later that deals with this comparative HALT purpose, and some things that you have to kind of keep an eye out for. That the HALT table has some non-uniformities to it, so I'll share with you information about that and how to manage that non-uniformity. HALT sometimes comes to us as a customer specified requirement. Hey, I've got to do a HALT test. My client said I have to do it. One of the things about HALT is it's not a passing test generally. The goal of it is to find failures. So we don't typically see HALT applied where you run it for 2 hours and the product has to pass HALT at 30 Gs for 2 hours. We generally, in fact, we almost never see HALT specified as a compliance requirement or a validation requirement. It's almost always used, again, in this sort of find failure sort of approach. And lastly, HALT is used to find the test points for a HAS test. We're not going to talk about HAS in this presentation. HAS is a manufacturing temperature and or vibration test using the same equipment, using the HALT machine, but it's used as a manufacturing screening tool. So after finished product is manufactured, it's brought over to the HALT machine, and we run this temperature profile, vibration profile on it, again, to try to find defects that may have crept into the design through variations in the manufacturing process. So find weak links in the production process. So all of these are very much qualitative tests. So yes, HALT is a good qualitative approach. It generally is not a quantitative test, a test where you can run it for some period of time and to be able to produce something that relates to like a mean time between failure or some sort of R and C reliability and confidence value. It's generally not suited for any sort of contractual compliance test, as sometimes are run in the military to demonstrate reliability growth. That is typically not an application for HALT. There are some HALT practitioners that try to create a little bit of a database of how products have managed HALT and collect that information, create a database, and then from that try to extrapolate out on that quantitative reliability. But it's not generally accepted to be a a test where you can run it, especially for the way that it's typically run, 4 to 5 days of HALT, and then produce any kind of meaningful reliability metric, something that's quantifiable. So again, HALT is very much of a qualitative test. HALT, right? There's a series of applied stresses that we have available to us, and they are temperature, hot and cold, vibration. Like I say, we can cycle power, we can change loads, to create different current draws on the products. There's a number of things that we can do, but we can't do everything, and products sometimes need to be evaluated for multiple stresses beyond just these. But before we talk about stresses, one of the things I think is important in understanding HALT is to take a look at product failure classifications. And one way to kind of make sure that you quantify this or understand it is when you're looking at your product and considering how your product operates in its environment, it's best to kind of look at, what are the failure mechanisms that are operating on your device or acting on your device to create these failure modes. And then once you understand that, you can define some accelerating stress to test your product and make sure that it's compliant. So for example, let's say that you had a cell phone and you drop your cell phone from about three feet, and sometimes it cracks, sometimes it doesn't. What if you had 100 different cell phones and you drop them from different heights? What you might find is that there's some particular height where, certainly they're going to begin to start fracturing. And so this might be illustrative on some sort of a, normal curve or a log normal curve, some sort of a distribution as a means to describe the overall strength of the product, right? That maybe you would find some average height at which products survive or which they fail. That would be your average strength, and then you might find some parts that can survive much more of a stress to them, and likely some products that can withstand much less of a strength, right? So product strengths kind of come with some sort of a distribution, around maybe a mean value. Right? So when you drop your cell phone, you're eventually going to find some particular height that you're going to drop it from, or you're going to crack that display screen. So the mechanical or the failure mechanism associated with that cracked screen failure is a mechanical overstress, right? The screen, the cell phone manufacturer, designers make that screen to withstand a particular stress, and beyond that, it's gonna break. It's going to fracture. So the failure mechanism in that mode would just be a mechanical overstress. There's more stress than the strength that screen can allow. Other types of failure mechanisms, again, thinking about maybe that cell phone. What about static discharge? If you pick up your cell phone, your body's carrying a lot of static electricity on it, and you touch your cell phone, you find next that your display is non-responsive. You do some failure investigation and you find out that there was a failure due to that ESD discharge. So that particular mechanism would be a dielectric breakdown at some point. And the way to evaluate that and to find what is the maximum overstress that part can fail would be to vary the static voltage potential that's on your test. Same thing if you've got a cell phone that's you're trying to protect it from water intrusion. What might be the process or this failure mechanism behind the fact that you're not passing a water intrusion test? Well, maybe it's a quality issue. It's some sort of dimensional tolerance problem where the product does not seal, it does not fit right, and that's really the cause of the fact that you've got water leaking into the cell phone at this point, is a dimensional mismatch or tolerance mismatch. And again, a way to kind of evaluate that going forward might be to apply more water pressure, submerge the device in more of a water bath, or putting more head pressure above that water bath to produce more pressure and try to press water into the device. So again, when you're evaluating what stress to apply for HALT, or how do these stresses work with HALT, you have to kind of come back to look at the failure mechanism, look at the failure mode, and then select the stress that's going to produce that that particular failure on your your product. So so there's going to be a series of, or a distribution of stresses from the users, and how those stresses overlap with the strength of the product. Where they intersect here, these are where you're going to produce some failures on the product. So, but not all stresses create overstress failures, right? Or not all failure mechanisms are based on strictly an overstress test. That some failure mechanisms are based on time, or maybe some sort of cycle-dependent relationship. So something like, excuse me, something that we see pretty often with HALT testing is intermittent connector operations. We'll be running along, and all of a sudden we're getting a loss of signal on the product. And what we'll do is we'll notice on the particular product that there's, we look at the connector, and we'll see on the connector that there's a little bit of marking on the connector interface here. And it generally is a little bit of a sign. It's often a fretting corrosion issue, right? Fretting corrosion is created from these micro displacements that occur when this male part of the connector interfaces with the female part. And with millions and millions of cycles back and forth, there's an oxide, right? You start wearing away that coating, and you create a little bit of an oxide, on there. That oxide then creates the an impedance, and you end up getting this high resistance here, and eventually to the point where there's enough fretting corrosion on there that you lose signal contact. So so when we see intermittent connector operation, we would want to diagnose the failure mechanism behind that. We would want to diagnose the failure mechanism behind that. And in a lot of cases, what we'll find is that's a fretting corrosion issue. And we can accelerate that fretting corrosion issue by applying vibration, which is pretty effective with the HALT style vibration. Other types of failures that we'll see might be a cracked solder joint. We might understand that cracked solder joint to be caused from some sort of a fatigue that's induced by the vibration, or maybe from some of the thermal cycling. So these tend to be very effective HALT stresses to apply. Vibration that creates intermittent operation at the connector, which has an underlying failure mechanism associated with fretting corrosion, or vibration that cracks solder joints, cracks capacitors off, larger inductors off, and the failure mechanism behind that is fatigue. HALT won't address all failure mechanisms. So for example, there's just a couple of failures that we see with electronics that really aren't effectively precipitated with HALT. So for example, if your failure mode is a shorted PCB trace, and you do some analysis and you find that there's some dendritic growth between traces or leads or contacts, that's a particular dendrite growth is a particular failure mechanism that's really not driven much by the type of stresses that come from a HALT test. What might drive dendritic growth would be maybe some humidity, some contamination on the board, temperature and voltage. That generally, there needs to be some sort of potential between these two traces, maybe some contamination, maybe some humidity, and that will drive this particular failure mechanism. Electromigration is another underlying failure mechanism that is pretty well documented for high current types of electronic products. You'll see them you'll see failures at FETs, other current carrying components. But again, electromigration is something that takes time and it takes elevated temperature. In fact, it may take weeks and perhaps months of time and high current to create that particular failure mode. So these would not be effective HALT stresses, but they are things to consider. So what, when we're doing HALT testing, when these stresses are applied, what are they most effective at finding? And, whenever you have a discussion on reliability or product testing, you always kind of talk about this particular illustration here. It's called a bathtub curve. And what this shows is, failure rate on this axis and time along this axis. And, early in the product development cycle, there are probably going to be more of these latent sort of design defects in the product. And so you do burn-in, you do HALT, you do other sorts of tests to discover these problems, fix them, eventually improve them, so that by the time the product is released, the failure rates are pretty well understood and corrected, so that the product is released and it has a constant failure rate that basically is due to random failures, random faults. But eventually, as time continues, some of those other sort of degradation modes, electromigration, dendritic growth, Kirkendall voids, there's a whole series where all of those tend to take, time-dependent sorts of failure mechanisms tend to add up, and eventually the product will wear out and fail at that point. But hopefully at that point, you've got to the really the end of the useful life of the product, and you've gotten some good value out of it. So again, where HALT stresses tend to find their best uses are finding these early failures, finding these product problems that can be fixed and rectified before the product gets out to its useful life. The value of HALT comes from high stresses, right? If you look at a stress life curve, where we've got the stress amplitude on the y-axis and the cycles to failure on the x-axis, over here, this might be where your normal life cycle is. That if you've got perhaps a lower stress, that you can get that product to survive for many thousands of cycles or tens of years. But in the test world, you can't wait 10 years of applying a normal stress to the product to get it to fail. So certainly in HALT, what we do is we test at a higher amplitude to create these faults in a much shorter period of time. So this is our goal with HALT, is to apply higher than normal stresses to try to accelerate these stresses and accelerate these degradation mechanisms and create failures quicker under high amplitude testing rather than what you normally would have during normal stress in the field. So this is a chart of a typical HALT test. We run this pretty regularly at Elite. This is taken from the General Motors, the GMW 8287 Spec, and it's a prescription for probably, I would say, most of our HALT clients. There's not a mill standard HALT specification. There's not an IEC HALT specification. HALT is something that's really tailored to the process. But here's an example where General Motors has accepted HALT as part of their early validation sort of approach, and they put it into a standard and describe it. So we use it here quite a bit. This is something that's publicly available. We suggest it always to our clients to download it and use that as a background document. But again, this particular sequence of HALT applies temperature in increasingly colder steps where we might drop down in temperature, dwell for 10 to 30 minutes, examine the product for any sort of an anomaly. If there's no anomaly, continue on colder with another dwell, drop down colder with another dwell, drop down colder with another dwell, until you reach either a lower operating limit or kind of the end of that test as you feel it applies to your product. At some point products might not be ever exposed to something down to minus 100 degrees C, but at some point we'll stop that test and either find a lower operating limit or just call it good enough. Same thing with the high temperature stresses. We would gradually increase temperature and dwell, always monitoring the product, looking for some sort of a fault, and seeing what we can learn about applying temperature, either cold or hot, individually. Generally, the next sequences involved a series of thermal shock tests, followed by vibration only. So we'll increase in amplitude of vibration, vibration alone, and then finally we'll apply vibration with thermal shock to see, as we reach some of these high vibe levels, is the vibration made even more stressful by applying it at high temperatures and cold temperatures. So this is pretty much the I'd say the boilerplate HALT specification, but in no means is it the test that has to be run or should be run. We always suggest that it depends on your product and what you're trying to learn about your device. That maybe maybe not all of these steps, some of them might have more value for you. This spec, again, you can go to Global Engineering Documents and you should still be able to download this GM spec. This is the one I would recommend if you're considering HALT testing. It's $36 from Global, and it would give you kind of this outline as well. So again, HALT, purpose of it is to not only identify latent defects, problems, lurking sort of issues and problems in the product, but also to identify, what are your operating limits, product spec. So the best place to start on there, what are your product specifications? What do you identify as the the temperature extremes? Maybe you've got something about a voltage limit for your product. What are those specs? And then using HALT to find what those margins are. So for example, we would lower the temperature of the product below the manufacturer listed specification and find out if there's an operating limit for cold temperature. For example, and when you would lower temperature to the point where a product is exhibiting some sort of an anomaly, we would note that anomaly at that low temperature. We would increase the temperature to see when and if the product recovers. If it recovers, then as we go lower in temperature again, that problem manifests itself again. Then we would identify that as the lower operating limit. We might even continue to even lower temperatures to find a lower destructive limit to, maybe this is something that we might see like an LCD display. On the other end, we would continue for the upper operating limit, whether this is temperature or vibration, and find an upper destruct limit, again, for temperature or vibration, or even voltage, whatever the spec is that we're trying to understand these margins. So the chamber itself, just talking about it and some of its characteristics, this is the one at Elite, and you can kind of see that this temperature has a vibration table. This is the table down here. You can see the impact hammers underneath the table with this guard off. You can see a series of heaters up above the chamber here. This is where we get our hot air from. And then here are the ducts that will duct in either the hot air or the very cold air that we get from our liquid nitrogen supply. So our particular chamber has a table area of about 39 inches across. Some of the temperature extremes that we can achieve in this chamber are listed here. Sometimes we can hit them, sometimes we can't. There's our LN2 tank, a little bit closer picture of the heaters. We can create some incredible temperature swings with this bank of heaters that are driven at 480 volts, 75 amps. We can produce a lot of temperature change and offset that with the liquid nitrogen to get some really severe ramp rates in temperature. So what is it about HALT that makes it somewhat unique? Again, the nature of this testing is called repetitive shock vibration. So you can see underneath our table here, this table is suspended on four corners by springs, and the HALT table itself is kind of manufactured as a, and I like to call it, an aluminum piece of Swiss cheese. You can kind of see that a lot of the mass of this table is taken out, because the idea is when these pneumatic hammers impact this table, that you want these hammers that they're arranged to impact the table in all different sorts of axes, and the fact that they're up on springs gives this table some motion and mobility. So what's created with this is a simultaneous 6-axis vibration. So there's 3 linear X, Y, and Z, and then 3 rotational axes of vibrations, like pitch, roll, and yaw would be the rotational. And for many applications, that's pretty valuable to have that simultaneous vibration. You don't have to repeat vibration in 3 axes. Really, you run the test one time and you get pretty equivalent vibration in all 3 axes. There's some difference, but it's relatively equivalent and relatively equal. The other thing about HALT is that the spectrum ranges from about 60 hertz to about 10,000 hertz, and that's good and bad in some respect. Good in that it gets to some very high frequencies, and there are parts on electronics that respond well to that higher frequency vibration. The fretting corrosion, for example, is really driven nicely by some of that high frequency vibration. But it does suffer that it doesn't have a lot of frequency energy, say below, excuse me, below about 200 or 300 hertz. It's a little bit more rich in frequency above 200 or 300 hertz, but below that, not as much, which has some, in some cases, some downside to it. The other thing that HALT does that makes it a little bit of a unique vibration is that it produces these very high G instantaneous accelerations. I mean, you have in this photo here, there's 6 different hammers that are providing these impacts on a very repetitive cycling. So you get some very high induced peak accelerations, and a lot of manufacturers find that those high accelerations do produce some effective failures on their products. Generally, a lot of those high G accelerations are a little bit more typical of what you'd find in the field. So there is some definite benefit for that too. One thing about a HALT table, right, it is this metallic structure that's being impacted by these hammers, and essentially what's happening is the vibration table is put into this resonance mode, and that helps us, right? So when we're at some of these nodes where that resonance is amplified, we get the benefit from that vibration. But you also have to be careful that when your product is in one of these nodes where there's a null, there's going to be less vibration. And we'll talk about the impact on that on testing when we test similar devices. So again, this is the characteristic of HALT. Here's a typical power spectral density display. Again, you'll see a lot of circuit board resonant frequencies that exist. Circuit boards have resonant frequencies generally, depending on the size and how it's mounted, maybe between 50 hertz and a couple hundred hertz. Components on those printed circuit boards tend to have higher resonant frequencies, and chip capacitors and die bond wires in microprocessors tend to even have higher resonant frequencies. They're smaller structures. So the effectiveness of vibration that you apply depends really on the character of the vibration that you're applying. HALT does produce vibration over a pretty wide range, but you can kind of see that it's in a little bit of these higher frequencies that the HALT vibration is a little bit more active. So again, kind of comparing this repetitive shock to other types of technologies. We have both here at Elite. We have a repetitive shock machine. We have our HALT repetitive shock. We also have a number of electrodynamic vibration tables. And so let's maybe kind of compare what these two machines do and how they might be helpful. We would recommend both as a pre-screening tool for a couple of different reasons. Certainly HALT, we like the fact that it provides the 6-axis simultaneous vibe that you can combine a very severe thermal shock with vibration, and you get the high G accelerations. We think that's a pretty effective tool. But some of the downsides of HALT is you have this non-programmable spectrum. You kind of get the random vibe that you get from HALT. You can't really change it too much. There's not a lot of displacement on that HALT test, only maybe a ½ inch in displacement, which really does kind of reflect in the fact that you don't get a lot of low frequency vibration. On the other side, with electrodynamic vibration tables, you can program exactly the type of vibration spectrum that you want. You can do that as a sign. You can record field random data and then run that on your product. You can amplify that to also kind of accelerate the test too. So an electrodynamic shaker provides this programmable spectrum. It provides a little bit more vibration at lower frequencies, and we'll talk a little bit later here that in some cases we can even model some of the or emulate some of the high G accelerations on our electrodynamic shakers that we see on HALT by using this tool from our vibration controller supplier. It's a product that they call Crotosian that allows higher peak accelerations to be put back into the vibe test. I'll mention just very briefly that there's a third type of vibration machine, and that's the servo hydraulic type, which we really don't necessarily have here at Elite in this fashion, but just keep in mind that there are 3 types of vibration that are available to evaluate product durability and reliability. As I mentioned before, when you look at a HALT vibration test, what you'll find is that, right, because the table here, this is a resonant structure. We've got hammers that are hitting beneath it, and what will happen is this table will resonate a little bit, and so we have to be a little bit cautious about where we put parts, and it's illustrated here where we placed three accelerometers, an X, Y, and Z accelerometer on the table. In fact, we put it at 5 different locations on the table, and then when we did that, we measured. We set the table to a particular set point, and then we measured the resulting GRMS values. So this set point control level, this is measured at an accelerometer underneath the table. So this is the Excel underneath the table, and then these values here are the GRMS that we're reading off of this accelerometer in the X-axis, in the Y-axis, and the Z-axis. So we can kind of make our own little sort of vector sum of this X, Y, and Z to come up with these values. And our particular machine has what's called a low frequency mode and a high frequency mode. And it does give us a little bit of adjustment to kind of move the character of that vibration around a little bit. But what we find is that, for example, if we take this location, here is our reference point, that we would find that elsewhere on the table in the low frequency mode, that we might, if this is kind of our maximum level here, we might see the HALT vibration here, maybe 20 to 23, in this case here, 23% less than what we saw it here, 16% less, 7% less here. So this was kind of our hot spot for vibe when we were running that particular demonstration. It'll change a little bit too, depending on the product and the fixture. In the high frequency mode, that sort of hot spot moves around the table because the character of that vibration and how the table is going to resonate is going to change too. So again, when we're doing comparative measurements for HALT, 2 different similar products, we want to make sure that we understand how the table is performing and maybe put that in a spot on the table where we can avoid some of these nulls and do a very effective comparative test. So moving on to HALT planning, it's a very important part of the HALT process. It's important to understand the product use environments, identify all the stresses. Your product might not see vibration. It might not see cold temperatures. So these are important bits of input to helping you design your HALT test and have an effective conclusion to it. If you have any field failure modes effects analysis, something that can give you some hint as far as how products you've had in the past have failed, that will help you design your HALT. Understanding the DUT specifications, physical limitations. Sometimes we apply HALT at high temperatures and we begin to melt plastics. We don't really want to do that to a product. It's not really a meaningful result, but knowing some of those limitations will help us craft the test to make it effective for you. Knowing what parameters to monitor. What are you going to consider a failure on your product? I say a lot of times when we test LCDs, we'll bring that LCD to a cold temperature, and eventually the liquid in the crystal will cool, and you'll actually see the LCD begin to get a little bit more sluggish, and eventually you won't see it at all. It's not really a failure. It's just kind of the bound of an LCD crystal. It'll be important to know what actions you're going to take when a failure occurs. Will you have a backup sample that you may need to put into the test if you have a non-repairable failure? What are your expectations for HALT? What are you really trying to find out from that test? These are all part of the planning process that, we ask our customers to look internally and kind of answer these questions. And so that when we meet and discuss our HALT plan with you, that we've got a good structure and a good test to go forward. We'll generally ask our client to define the test using a chart like this to identify some of the endpoints of the test, what increment, what dwell time. These are the sorts of things that you might know about your product. How long do we need to dwell to really see the product respond to the stress? So we'll work with our clients to fill out a HALT test planning sequence like this. And next, work with the client to help prepare the test item too. So there's a few things here that we want to point out. Preparing the sample to get the stresses to it is an important part of this. And two things to consider. How do you prep your item for temperature and temperature shock, and how do you prep it for vibration? So, for example, we took this little scenario where we got some relatively cost effective residential thermostats, and we wanted just to do a little bit of comparative assessment on these, and taking a look at temperature first. So you can see there's a thermocouple coming into this little thermostat, and we've got the thermocouple attached to the printed circuit board in there. And in this case here, this particular thermostat, it's pretty well sealed up, and as compared to this one down here where we inserted that thermocouple in close to the same spot. But in this one here, we tried to cut away as much of the plastic as we could without really affecting the performance of some of these buttons, because we needed these buttons to evaluate the product. So here you go. This is a little bit of a example of a well-covered product versus a opened product, and what might we expect as to how effective the temperature is at getting into these boards, and making the temperature change at the board significant and as effective as possible. So you can see the layout of the products relative to the heating ducts that we have, or the ducts that we have here that are going to bring in hot air and cold air. And I guess this is what we're trying to illustrate here. This is our thermal shock profile, and the purple line here is the actual duct temperature. You can see that we can get some very, very quick thermal change rates with that duct air. The unit with cutout holes, we were able to get about 75 degrees C per minute temperature changes. This is actually on the printed circuit board. Thermocouple on the printed circuit board is measuring that. So this is the thermostat with the cutout holes. The thermostat without it, we're only able to get about a 40 degrees C per minute ramp rate, which may not seem like it's that significantly different. But again, the point of this is that when we talk to customers about a HALT test, preparing the sample to try to get these stresses as much to the product as we can, as much to the circuitry as we can, if that's the goal, is to stress the circuitry, is to make sure that there's adequate ventilation and a way for that air temperature to get in there quickly so we can get these quick ramp rates. Similarly with vibration, we want to know if here's an accelerometer that's telling us how much vibration is present at the standoffs, how much vibration is transmitted then to maybe a fixture plate that we have on there. What's the best way to design a fixture for that? And here's a little bit of an example of the effect of fixturing on vibe. So here we've got this small plate. We've got a little bit larger plate that gets bolted down to more of these standoffs, and then we've got an even larger plate that gets bolted down to even more standoffs. Remember that this vibration table is a resonant table. It's trying to shake. It's moving back and forth. So the larger the fixture is, the more massive the fixture is, and the more that we bolt that fixture down, the more we constrain the movement and the flexing of this table. So we prefer to have smaller footprint fixtures rather than larger fixtures that constrain the table. And that's illustrated here in for the small plate, when we set the control accelerometer to achieve about 64 Gs RMS. And then we look at the responding accelerometer, excuse me, the responding accelerometer, and we look at what that transmissibility is from the control accelerometer to the accelerometer mounting on the fixture. You'll see that on the smallest plate, this is where we get our highest vector sum GRMS acceleration, and as the plate gets larger, you can see that you're getting less of a vector sum. So again, we're dampening out some of the vibration by using a heavy, larger, more massive fixture that clamps more of that table down. So what we look to do is to, is to also not only the fixture size, but are we going to test a product just as a printed circuit board, or the product in its housing? So again, if we take the sample out, we take the printed circuit board out of this thermostat, and we try to test them in a comparative manner, side by side. How effective is vibration getting to this printed circuit board versus how effective is acceleration getting to the printed circuit board when it's mounted in this little thermostat here. So you can see the accelerometer on the board, you can see the accelerometer down here on the table, and then you can see the accelerometer here that's mounted directly on the board. But this board now is within this thermostat housing, and how this board is constrained in this housing is it's basically just more or less a snap fit. There's not a very secure hold of this printed circuit board to this housing here. The housing is bolted onto the metal fixture down at the bottom here. But again, there's a lot of attenuation of the vibration between the fixture and through this plastic case in here. And again, the point being that, as you can kind of see here, that when you have the PCB mounted separately to the fixture, in this case over here, that when you look at the vibration measured on that standoff, if you get a vector sum here at when our table is set at 10 Gs, you would get a vector sum here on the printed circuit board of about 27 Gs. I'm sorry, at the standoff, it's 27 Gs, but on the actual printed circuit board, we're measuring 14 Gs in here. So we're basically about half as much vibration on that printed circuit board than what we're actually getting on the standoff. But if you compare that in this scenario here, where again you're measuring that standoff and you're comparing that to what you're getting on the PCB, you can see that there's quite a bit less that gets here. So again, having good transmissibility between the fixture and the printed circuit board is critical. So a couple of other fixturing suggestions here is, this is a relatively typical approach where we'll, testing this display, we'll have some bar clamps across here, a couple of clamps to hold down the edges. Printed circuit board, we would want to mount, if there are standoffs for that printed circuit board, we would want that mounted directly to a 4x4 plate. That's a very effective way to do it. Again, some other typical fixturing, effective fixturing approaches. Again, with the product, the printed circuit board completely exposed to the temperature environment. So this is really kind of a perfect scenario to use HALT stresses to get those stresses to the part and make it just as effective as possible. If you can't get to the printed circuit boards, we tend to use bar clamps wherever possible. These tend to be pretty effective, very quick approaches as well. Again, kind of avoiding a heavy, massive fixture in the test table. So kind of finishing up here, maybe in the last few slides, just wanted to connect you with some, how effective are these HALT stresses to find product failures or find product weaknesses. So again, here's our cold step, our hot step, our thermal shock, vibe alone, and then the combined. And going back, I don't know, this is about maybe a year's worth of HALT testing, looking back at previous reports. We can kind of look back in 15 total tests, looking back at how that product managed itself in that HALT test, that out of 15 reports that we examined, in 12 of those cases, there was no fault found when we did a cold step. We got down, minus 60, minus 70, minus 100 degrees C, and there really wasn't an issue going cold. Looking at the hot step stress test, there were 10 situations 10 out of 16, where we really didn't find any kind of a high temperature related fault of any sort. Thermal shock, 13 out of 16, no fault found on those. However, when you come to the vibe and the combined vibe with thermal shock, you'll see that there were far fewer no fault found situations. So what this tells us a little bit here is certainly, what is the effectiveness of a cold step stress, effectiveness of a hot step stress. Certainly there are faults that are found with those, and it's valuable information to a manufacturer to find these things, but they tend to be perhaps not as productive as the vibe and the combined vibe with HALT. So taking that information, we would suggest using that as far as part of your planning process. Again, it's important to understand how your product's used, know what kind of failures you might expect, and then focus the test on accelerating those mechanisms, those failure mechanisms, looking back at previous failure data that you may have, understanding the specifications versus what are the physical limitations on your part. We talked about this a little bit earlier. How do you plan for that? And then, define the test based on the relevant stresses that you want to apply, right? So, and there's a couple of ways to do that, right? You can run an accelerated life test either in the HALT chamber. You can also look at some alternative testing to arrive at HALT results, right? So this would be an approach where maybe you're not using the HALT chamber. So, here at Elite, we would want customers to consider both to help them find, those sorts of failures that could compromise the reliability of their products. We think you might have to look at both approaches. So again, if you're going to use the HALT chamber, determine, does a cold step make sense? A hot step, thermal shock, are any of these tests going to bring you value? Are they representative of your environment? Would you need to know some of these operating margins? These may be some of the things that you can do internally. and you don't necessarily need a HALT chamber for. Will the 6-axis combined temp and vibe alone work best for you? That might be the part of the HALT chamber that you find most effective for finding the issues with your product. But consider some of these alternative tests as well that certainly manufacturers in all different industries rely on other types of tests to help them with these long-term kind of time-dependent failures. So thermal fatigue, we see a lot of manufacturers that might do, tens, hundreds of hours, maybe 1,000 hours of thermal shock testing. And the reason that they do that is a very effective thermal fatigue test for finding faults at solder joints. You wouldn't find through a thermal shock test of 5 cycles, the amount of damage that you would, or that you might not get the number of cycles to create the damage in a HALT test that you may need to get by doing a longer duration test. But there are test acceleration models that can be applied. So for example, the Coffin-Manson is a very commonly cited acceleration model to evaluate thermal fatigue. The Arrhenius relationship for high temperature degradation. So this would be something that you might want to run to evaluate some of those electromigration types of tests. You can also accelerate vibration by taking a field data vibration or maybe your qualification vibration test and just amplifying or increasing the level of that based on a power law stress life relationship. And as I mentioned earlier, here at Elite, we do have the ability to run a electrodynamic vibration test with Cartosian control, which tries to emulate the vibration, the high acceleration vibration that you get with HALT, but it's basing that on a, perhaps the field data that you collect on your product. So finishing up over here, some final recommendations. Again, prepare your samples for testing, optimize your fixturing. Generally, we need 1 sample to provide the HALT data. It's better to have more. I mean, certainly in some cases where the sample is kind of a one-of-a-kind product, it's an expensive product, you might only have 1 sample, but you need to have the ability to remedy any sort of errors that you see on the product. We encourage our customers to be on site for HALT and to participate live. It's the most effective way to get information back to the designers, understand the product, how it responds, and how to assess future modifications to it. And then certainly having some understanding of how you're going to improve the design from these results, and then possibly rerunning the test to make sure that those changes that you made have indeed improved the product to the point where its reliability has been enhanced. So I guess to conclude here, we always look for an opportunity to work with clients to find the right test to apply. Sometimes it's the complete HALT sequence, sometimes it's HALT plus some adjacent tests, but we're looking to find the correct mix of tests to apply to get you the information that you're looking for. So I'll end there, and we went a little bit long here, so I will unmute so that if we have any questions from the audience, love to hear them. We will send a copy of the presentation to all of our attendees so that you have it. And if you have any questions that you want to bring up separately, certainly give me a call, or any of the folks here at Elite on our team a call. Be more than happy to answer that for you. So anybody have any questions for us today?
Hi, Steve. This is Nick Hackenbach over at Molex. First of all, thanks for the presentation.
Sorry,
a lot of good information here.
Sorry, Nick, can you ask that again?
Yeah, can you hear me all right?
I sure can. Sorry about that.
No worries. I was just saying, really appreciated the presentation. A lot of good info. One of the questions I had actually was about controlling with the chamber when it comes to vibration. I had read somewhere that there was such thing as a multi-zonal control for HALT chambers, and I was just wondering if you had heard of that And if you guys have that, or is it more so just knowing the different, as you would call them, vibration hotspots on your table?
Yeah, thanks, Nick. No, I know that there are manufacturers that try to create a vibe table that can do multi-zone control. Our chamber does not do that, so we don't have the ability to kind of balance out the table. It's you know, we kind of get what we get from the structure of the table. So that's right. That's indeed what we have to do, is we have to kind of understand. And again, this really matters when you're doing a comparative assessment, knowing what that difference is in the placement of products on the table. When it's really just I'd say more of a typical HALT test, where we're trying to test one device and we're trying to identify its particular product faults. We'll try to get that product right on where we know our hotspot is, just so that we get the most benefit out of the HALT. But we understand too that as soon as we kind of bolt it down, it's going to change a little bit of the dynamic characteristic of that table, and it might squeeze it around a little bit more. But in that mode, when you're testing just a single sample and not doing the comparative test, it really, you know, the fact that the table is zoned in different areas, it's not as impactful. But yeah, you know, certainly when it is a comparative test, where you've got multiple parts on the table, you do have to pay a little bit more attention to what each of those locations are seeing, and account for that difference in the data a little bit too.
Great, thanks. And just one more question about control. Do you ever have any problems with ground loops that you would see similarly with an electrodynamic shaker if the systems weren't on the same ground?
No, I can't think of situations in HALT where we've had to contend with ground loops. No. And even on our ED shakers, you know, I guess if we're dealing with that, we generally do figure out a way to put in the isolation that we need to prevent that on our ED shakers. But that's not an issue that I've heard of in all of the years that we've been doing HALT, where we've had to contend with ground loops, and whether it's on the product or any sort of instrumentation, that we've had to contend with that on HALT.
Great, thank you.
Thanks, Nick. Okay, you guys, hey, I appreciate it. I appreciate your attending our presentation today. We always look for feedback on this presentation, on the content, on you know, how this may have helped you. So if you have any feedback for us, that would be great. Send us an email. Would love to hear your questions if you have them. If you want to send them by email instead, or just give a call, that would be great too. All right, well, thanks everybody. Stay in contact. We'll have news on future presentations, future webinars on different topics, and we hope to see you all back on the next one. Thank you.